In this presentation, we're going to have a look at the concept of a blockchain. Some might also call it a distributed ledger technology, or DLT. And I'll try and explain each of the core concepts involved in blockchains and distributed ledger technology. For this, we'll look at some cryptocurrencies as an example of a usage of blockchain, but certainly not the only application. We'll look at the Bitcoin blockchain and see how it's made up, then the concept of miners and mining of cryptocurrency, then on to Ethereum, the usage of digital wallets and the integration of smart contracts, and then on to what are called permissioned ledgers, and then finally a little bit on digital signing. So overall, what we have is that we have blocks. So these blocks contain a range of transactions. So they might be cryptocurrency payments, or they might be messages or something like that. And then what we do is that for each of the blocks, we have our data elements, and then we hash each of the data elements, our transactions, and then we'll hash again and hash until we get what's called a root hash. This is known as a Merkle tree, and this is the root Merkle hash here. We can then add that hash along with our transactions into a block. Then we can take the previous hash, the previous root hash, and then the next block's hash. In this way, we can chain the blocks together to make it immutable. So it's not possible to change any of the data because it would change the hashes within a certain block and also its linkages onto the other blocks. So it's with the Merkle tree that we can actually make sure that our data is both trustworthy and also immutable, that it can't change once we create our block. This block here is known as the genesis block, or the initial block that we create. So when it comes to cryptocurrencies, we need to look at our existing payment system. For this, Bob trusts Bank A, Alice trusts Bank B. If Bob wants to pay Alice $10 in this case, then he needs to get her ID and her sort code. Then the ledger on Bank A will be reduced by $10, and the transfer will happen between the two banks, and Alice's ledger will show that she's up, or Alice's bank's ledger will show that she's up by $10. And some started to question why we need the intermediaries of the banks. Why not let Bob and Alice communicate in a peer-to-peer way? For this, we could have an open ledger, and we can use public key encryption, such as using the private key, to be able to sign for a transaction, and then everyone can prove that Bob was the signer with Bob's public key. So in this case, he could commit a transaction to a distributed ledger or a blockchain. We can have our transactions within each of the blocks. And then we can use the digital identity that is associated with Bob and the digital identity of Alice, so that the ledger will contain a transaction that will show that Bob signed off a transaction from himself to Alice for 10 Bitcoins in this case. But we have a problem here. What happens if, when we're creating the block, Bob goes and spends his money twice? So we need to avoid the double spend to make sure that Bob doesn't take his cryptocurrency and spend it twice before anyone actually notices that he spent the first time. We also need to make sure that Bob has enough cryptocurrency in his account. So the miners need to take the transactions and make sure that there is no double spend and that there is enough funds to pay for the transaction. So these miners all get together and then they will create a consensus as to what the transactions were at a given time. In the Bitcoin network, this is around 10 minutes. Every 10 minutes a new block is created and the miners will agree on the consensus. One miner will win and create the actual block itself and be rewarded with a mining with a reward. And it all started in 2009. A person called Satoshi Nakamoto. This isn't Satoshi Nakamoto. This is a person whose name is Satoshi Nakamoto, but the person who created Bitcoin is not this person. One thing is for sure, that the first person to actually mine for Bitcoin with the very first block was Hal Finney. And he mined this block here and created it. This is block 0, the Genesis block. And we can see here that he was rewarded 50 Bitcoins for this mining. Along with this, we can see here that the current hash is here for this block. And the one thing that's strange is there's lots of zeros at the start. We'll see where this comes in a little minute. But basically, the miner must find the nonce value, which will create this hash here. We also have the previous block. There wasn't any previous blocks, of course, so it's all zeros in this case. And here is the hash of the next block to make it immutable. We can see that the time that was created was the 3rd of January 2009 at 6:15 p.m. here. And there's the size of the block that was actually created. And there was only one transaction in there overall. And basically, it was a bit of a hodgepodge of cryptographic methods that had been created over the 1970s and 1980s. And it was led forward by some extent by the cypherpunks Eric Hughes, Timothy May, and John Gilmore, who said that there must be a better way to actually transact financially rather than using fiat currency. At the current time, the actual block size is around 550 gigabytes, so that each Bitcoin node will have to store the whole of the blockchain. But the advantage with a blockchain approach is that we could destroy each of the copies of the blockchain. As long as one copy exists, we can replicate it again. And overall, 21 million coins were minted initially, and that's all the coins that there are. At the current time, there has been 19.8 million coins in circulation, but once we get to the 21 million, there will be no more coins left. Okay, this shows us where we are. We can see 651 gigabytes of storage. We can see it's went up linearly over the time period from 2009. This was the white paper that Satoshi created, and he or she defined in there a proof of work method where the miners have to do some work, and it is this work that has a cost, and where it should be too costly for miners to take over the control of the network. And under the hood, it was based on elliptic curve cryptography, or ECC, which was created or invented by Neil Kobolitz and Victor S. Miller. And with this, we have the concept of an ECDSA digital signature, which is used to be able to sign for transactions and also to verify them. Okay, and there are various generations that we can have for Bitcoin, for our blockchain distributed ledger methods. The first generation was very simple, such as Bitcoin, Litecoin, Monero, and Bitcoin Cash. And they had high transaction fees and long transaction times. As I said, about 10 minutes. Second generation came along, and we started to see smart contracts integrated into them, and where we can actually add coding into the operation of the distributed ledger. Then the third generation uses direct acyclic graphs, which allow us to be able to create almost instant consensus. Examples of this is the IOTA ledger. When it comes to transaction fees, then Bitcoin and Ethereum are increasing in their speed, but obviously they still struggle against the traditional fiat currency methods such as Visa. And overall, there are many different types of cryptocurrency coins that we can have. As I said, Bitcoin and Ethereum, and these are some of the other ones here. Each have their basic characteristics that we would see from our cryptocurrency. Okay, so if we just have a look here. And here are some of the cryptocurrencies that we have. We can see it keeps going on. It may not be possible to be able to cash in these cryptocurrencies through an exchange. But overall, we can see here Bitcoin has the current market cap of about $1.6 trillion here. And there's the number of Bitcoins that are in circulation. Ethereum comes second, quite a way back from there. Tether, then we have Ripple, Solana, and the US tethered coin. So with a tethered coin, then there will be stability in the price. We can see that it should always be worth $1 here, where obviously the non-stable coins will fluctuate related to supply and demand. Okay, but you can see there are so many coins that are possible from there. Okay, so there's some of them there. So now let's look at some detail at the Bitcoin blockchain network. Okay, so as I said, it was created in 2009 by Satoshi Nakamoto. It has no centralized government organization that regulate it. It uses a mining process to be able to create the new currency and to create a consensus. We can have a smaller subunit of Bitcoin called a Satoshi. And it's limited overall, so we can get 21 million Bitcoins, and then there are no other Bitcoins created. What basically happens is that the miners are given a reward, and every so often the reward is halved. So this will de-incentivize the miners over time. So it started off at 50 Bitcoins, then went to 25, and it's now down to 3.125 Bitcoins, and it will half again at some time in the future. And there are many different types of cryptocurrency that we can have: Ethereum, Ripple, Litecoin, Monero, and so on. Okay, so here's the Genesis records that we saw earlier. So this is record 0 from there. There's the time, and we saw the hash method there. There's the Merkle root that we have. This is the nonce value that's going to create the special hash that we need in there. And there's the reward that the miner will get for creating this block. You can see it's a very small block that was created in this case because there was only actual one transaction in there. And this happens roughly every 10 minutes or so, a new block is created. Again, there's been some very large transactions we can see here. So in this case, we have a massive transaction here of 180,773 bitcoins for this transfer here, and there is another large wallet there. Okay, so what we have is that we have an address that's allocated to someone, and we'll look at that address in a little minute from there. Okay, so obviously there's been a great deal of fluctuation in the price of Bitcoin related to the supply and the demand, but this shows just over 1 day at the current time of this presentation. Then it was $85,000 in there, but we can actually look at the current status if we went for the whole time. So this is over the years. We can see it's generally increased in value. It's around 2021. It had a big fall, but has come back from there. Then these are the blocks that are actually created. So inside each block, we'll find there are a number of transactions in there. So these are the transactions here, and we can look at each transaction. So this is pseudo-anonymized, where it would be possible to link someone to this wallet identity from there. But we can see here there's the actual Merkle root here. There's the nonce value that we see. And well, it gives us the total amount of transactions from there. Okay, so we can actually view any block through this link here. When it comes to trading, the amounts of trading, you can see it tends to vary very much around the volatility of the market. So this shows the actual market price, and this shows the confirmed transactions. So when we see a peak, then it's typically that the price of the Bitcoin is falling in some way, and there's lots of activity. So we can see this chart here. Okay, and here is it for all time from there back to 2009. But we can obviously zoom in to look at the recent transaction amounts. Okay, so at the current time, the cap is around 1.6 to 1.7 trillion dollars overall. We can define the high and the low. This is the total number of Bitcoins in circulation, and there is the total that we can have, which is 21 million in there. Okay, and there's the Genesis block created there. The way it works is that we initially create a 256-bit private key. So this is the private key value that goes into the elliptic curve cryptography. This is then converted into what's called a WIF private key, which is then stored in Bob's wallet. Overall, this is a base 58 conversion of this private key into this format here. Base 58 is used because there are certain characters that are not so easy or could be confused together. So we drop some of the characters that we would have in base 64 to give us base 58. We then take a signature of that to give us a public key point with elliptic curve DSA. We take a hash and then another hash and then base 58 again to give us our public key. So one form of a Bitcoin addresses begins with a 1 that we'll always have. And overall, there are 3 main addresses that we can have for Bitcoins. We can see some of them here. So if we look over here, the ones that begin with BC are the most up-to-date format, or the BEX 3032. So we can see this address here. But we'll get ones that start with a 1. And that's the older format, the base 58 format that we just saw from there. And that's the P2PKH format. We also get another base 58 format, and this begins with 3. So perhaps we can see one here. So we can see this one has a 1 overall. But most of the ones here are the more modern standard. For this, it starts with a BC and ends with a P or a Q at the end. Okay, so we should be able to see examples of this. This is actually Satoshi Nakamoto's wallet here. Okay, and you can see that there are there's a lot of Bitcoins still left in Satoshi's wallet here. At the current valuation, about 8.7 million here for this address. But the key thing we can see here is there's the 1 at the start, and this is this type of address that we have here. For the second type, then we see a 3 here, and this is P2SH format, and there, and we have the 3 at the start there. Okay, so the total address here, if we wanted to copy it, we can just copy it from this address from there. But each wallet will actually show us all the transactions that have happened and the total amount of volume and the number of Bitcoins within inside the wallet. Nothing is kept secret. And this is one of the more modern methods, which doesn't use the base 58, and it's the BEX 32 format here. We can see here is the BC at the start, and then there's a Q at the end. And again, we have all the details within inside our wallet. Okay, so just to show what the keys look like, there's the private key. The public key is a public key point. You can often identify it with a 0,4, which is an XY point on the elliptic curve. There is a WIF that's stored within inside the wallet, and that then generates the address that we would use for Bitcoin. And then a signature itself has an R and an S value to produce the elliptic curve digital signature algorithm method. Again, basically what happens is that we have Bob is creating a transaction for Alice. Oh, sorry, Alice is creating a transaction here, and she will sign this with her private key. And within inside the transaction, she will point to Bob's identity and then sign the overall transaction with her private key, and then everyone can prove that transaction with her public key. So now let's look at the mining process and what's involved. So with the mining process, we want our miners to be able to agree, create a consensus as to what the transactions have been within a block, and then work out the hash that's required for that block. The hashes will then chain together to create our blocks and for it to be immutable. So overall, there are massive mining factories set up. Usually these need GPUs to be able to run them. If we look at a more modern share of the mining, we actually see there are not so many mining pools around, but in 2018, there was actually quite a few. So what we need to do is avoid the security weakness as to when one mining pool takes over 51% of the whole of the network, they can actually start to define the consensus for the transactions. So if we have a look now, this is over the last 4 days, and we can see over the last year, this shows you the mining pools that have been successful in creating the blocks. Each mining pool gets a reward if they can find the right nonce value that's required for the hash of the block. And overall, the difficulty of finding that nonce value increases due to this hash rate. So this is because hardware gets more powerful each year, so we need to make sure that it gets more and more difficult for the miners to be able to find the hash values. Okay, and the way it works is that we actually define the number of zeros that are required in the hash. So the miners must find the nonce value that when we're creating the hash, there will be a certain number of zeros at the start. So each of these miners will race to be able to find the hash value that works with the required nonce value. Okay, so there's one example here of a block, and what we should be able to see. So there's the reward that was generated for that one. There's the Merkle root, and what we want to find is the nonce value. Okay, so for this block, then the miner has found this nonce value here, which has created this hash value, and we can see here there are a number of zeros at the start, and we should be able to look at that block. So here it's here, and you can see here there are a certain number of zeros there, and obviously the miner who found the right nonce value was able to get the right number of zeros there. Okay, so now let's look at Ethereum, not Ethereal. We're looking at Ethereum now, and this was a new type of blockchain distributed ledger technology that was created to integrate the concept of smart contracts. It was co-created by Vitalik Buterin in 2015 and integrated the concept of smart contracts. Unfortunately, after about a year, it was hacked, and there was a fork of the Ethereum blockchain into two. This is proper Ethereum, and then there's Ethereum Classic. And the way it works is that rather than having this large-scale proof of work where the miners have to find a hash value for the block or the nonce value, then miners will do some work. So when a transaction comes in, they will do some work to make the blockchain work, such as running a smart contract or deploying it, and then they will be paid in terms of a gas value. So the gas value relates to the amount of work that they will actually do. So it's an incentive to be able to create miners which are rewarded through giving them gas, which relates to the Ether cryptocurrency. Okay, so we have the concept of a gas value, and the amount of work that's done relates to performing a symbol Kitcha 256 hash value. Okay, and then we have 30 gas elements related to a single hash. Okay, and the reason that we have the charge of the gas is to make sure that the work done is minimized as much as possible. Also, the amount of data that's consumed by the miners is also constrained, because the larger the data, the more gas that the miner will charge. So when the transactions are being completed by the miners, they will work out the amount of gas that they've consumed, and then that will be credited to the the entity which is asking for the transaction to be consumed. But they will only charge for the amount of work that they've done. It may be possible to advertise for some work to be done to the miners to incentivize them, but they will only actually charge for the work that they have completed. And we can also split the Ethereum cryptocurrency into smaller elements. So how does this integrate in with our users? Well, the way that we normally do it is with a digital wallet. And one digital wallet is MetaMask. So MetaMask is available on mobile devices and also on web browsers. With this, we can connect to the Bitcoin or the Ethereum network. But normally when we're developing programs, we connect to a test network. So an example that I've actually given in a related video, I've shown how we can use the Sepolia test network to be able to integrate with cryptocurrency. Okay, so if you want to set up your own, you can set up with these details here, and then we can examine the actual blocks that we created using this link in here. So for this, we create an account, and this will create our public identifier in Ethereum. With Ethereum, it's a simpler address that we just have a public key value, and we will store the private key in a trustworthy way that nobody can actually see. The wallet itself will tell us how much cryptocurrency that we have in the wallet. But obviously we need to look after our private key. So if we lose our private key, then we need some way to be able to get our wallet back again. The two main ways of doing this is either for us to get the hexadecimal code that we have. So in this case, there's a hexadecimal value, and when we're importing our private key, we can give this hexadecimal value. The other way is that we typically will have 11 words and an 11-word phrase. It can be larger than that, and that 11-word phrase we can write down and keep secure, but basically that will create the private key that we need. So it's important that these are kept secret, but it's important that we have a backup of our private key just in case we lose our digital wallet. Okay, and in the associated demonstration, I've outlined how we can use the Sepolia network. So what Ethereum brings is the concept of a smart contract. With this, we have a public contract that can be deployed using bytecode. So we take a programming language called Solidity, and then we compile to give us a bytecode that can run as a contract inside the blockchain. So everyone can see the smart contract and its details, so there is nothing hidden in there at all. But it basically enacts a contract between, say, Bob and Alice in this case. So this shows an example of a Solidity program. It's quite simple, looks a little bit like JavaScript, but we have our functions and the contracts and so on. The way that we can create our bytecode is using Solidity. So this is a Solidity example here, and the Solidity is then compiled into bytecode that's then deployed onto the smart contract. So in this case, here's my account. I'm using MetaMask. So I'm linking my account to the bytecode that's created so that it can actually interact with the blockchain. Okay, so if we just open that up, this is what's called remix.ethereum.org. And for this, we can store our smart contracts. So this is just a simple smart contract here to add two numbers together, multiply them, subtract, and so on. So once we have this, then we can go and we can compile our smart contract. It's important that we note what the version is of the compiler that we're actually going to use. In this case, we're using 0.8.26 for the compiler, and we should be able to compile that. Gives us a few warnings, but everything should be fine. We can then go ahead and we can then deploy that onto a public blockchain or onto our own test network. Okay, so we can select each one here. I can connect to my MetaMask wallet, and we can see here there's the identity of my main account here, and I can then deploy that onto the test network, the Sepolia test network. So in the related video, I've got an example of how to create a smart contract, and also how to create what's called a non-fungible token. Okay, so the ledgers that we've looked at up to now have been what are called permissionless ledgers, which means that anybody can go onto the ledger and create their own wallet, their own identity, and to be able to transact. That doesn't quite work in some corporate examples. And with this, we need a permissioned ledger. With a permissioned ledger, you need to have the right credentials to be able to use the ledger. And one of the best examples of this is Hyperledger Fabric, which is an open source system, and it's private and permissioned. So this shows the comparison between the two types of ledgers. We can see here we use Solidity for Ethereum, and for this we use Golang, Java, and Node.js. So often it's a decision as to whether we go for permissioned or permissionless. Within Hyperledger, there are a number of packages we can use. Hyperledger Indy is used for decentralized identity. Hyperledger Fabric is used to be able to create a distributed ledger technology. And there are other tools, libraries, and so on that can be integrated. As a last little element of our work, let's look at some basic digital signing. So with digital signing, what we're able to do is to be able to create a digital identity that will actually define a data object that we can sign with our private key. So this was an example flow that was used around COVID-19 times for the European health passport. With this, we have a JSON schema. This would have been healthcare data schema. We then add our data from the healthcare repository to create our JSON document. We can then compress that into some sort of binary format and then sign it with our private key. So this becomes the proven entity which will sign the data that we can trust and that we can verify with the public key. We can then produce, in this case, a QR code that could be actually scanned. So this was an example of a healthcare passport here, and this actually defined the vaccination status of someone and the related data for the individual. So this is a JSON type format where we have a key and a data element. So basically what happens is that we take our JSON data, we then can sign that by a trusted entity with the private key. So when that is then transacted, we can then check and verify the signature using the public key of the signer. Okay, so that's been a quick overview of blockchains and distributed ledger technology. Thank you.